Hi everyone. So we're continuing through section 2. This is going to be the last section in chapter 2, and then we'll move into chapter 3 where we'll talk about linear models. But right now we're going to talk about the general subject of mathematical modeling and just give you some more examples of what it means to mathematically model something. So here I've just got the definition of a model. You could probably come up with a reasonable definition on your own, but here's our definition. So it's a representation of an object or a process that highlights its most important characteristics. Now, what I would like to point out in terms of a model is that the model is not the original object. It's kind of like saying the map is not the territory. There are things that we either deliberately leave out. There are things that we may accidentally leave out. But we have to make simplifying assumptions, and that's kind of what this is talking about. So those are things that we deliberately leave out that basically make our model computable. If we put in too much detail, then it'll be too hard to work with. It's kind of like painting a picture. If you're going to paint a picture of someone and you're only going to use 3 colors, then you're going to be somewhat limited as to how much detail you can provide. But if you're going to allow yourself to use any possible color in your color palette, you could get a very accurate picture, but, well, it'll be more difficult because there will be more choices you have to make and more complexity. So somewhere in there's a balance between how much detail we're going to use and how much simplicity we want to have. Okay. There's a nice picture to kind of illustrate the idea of what we're saying. But let's look at an example. So this is an example that's about what we call projectile motion, in the sense that we're throwing something either off something or into the air, something like that. In this case, it's a baseball, and we're dropping it from the top of a 5-story building at time t equals 0. And then we've got our stopwatch, and we measure the height from the ground at the given intervals of, well, it looks like every third of a second, right? So 0, 3, 6, 7, 1 second, 1.33, and so on. Now, we can make a scatter plot of this, and you know how to do that. We would enter this data. This would be your L1 data. This would go into L2. Then you turn on stat plot. Let's say stat plot. That says press y equals, but we should really say, I'll just show you. You don't just press y equals, you press second y equals, and then you can turn your stat plot on. Okay. And do zoom stat, and then you'll get your picture. Okay. So that would generate a nice scatter plot of this data, and you can see here that it is a function of t. It does pass the horizontal line test. And so a mathematical model would be to take this data and then to come up with some kind of symbolic function that sort of followed that pattern. Okay. And in this particular case, you always kind of want to name your function, if you can, something that's evocative of what you're actually studying. So in this case, I would say it's h of t would be a good choice for height of the ball at time t. Okay, so I'm skipping a bunch of stuff here because I wanted to get to the function. So you see now a function, h of t equals negative 16t squared plus 49, and I've graphed it on the screen. You could do the same just by entering this as y1 and graphing it on the scatter plot, and you see that it's a pretty good fit. Now, it's not perfect, right? It kind of misses this point here and misses that one a little bit. It goes through that one, but it's approximating the general behavior. So of course the $1 million question is, where in the world did I get this function from? How did I come up with it? I'm not going to answer that at the moment. I'm just going to say, look, this is a you get this for free. Okay, so now the purpose of this course is to study how you generate such functions, or at least that's one of the purposes. But we'll get to that later, because the other thing you want to be able to do is use the functions once you have them. So this is a quadratic model of projectile motion. Let's assume that you were given it, and now we're going to use it. Okay, so let's talk about how we can use it. Couple of things. Let's talk about, we've already discussed how it does pass the vertical line test. Let's talk about these 2 bullet points down here. H of 1.75 equals 0. Okay, so I just want to take a moment just to talk about what the relevance of that is, and why we might be interested in it. So if I go back to the function, so what that's saying is that right here, that point right there, is that has coordinates 1.75 comma 0. That's what we call, because this is intercepting the x-axis. This is the x-intercept. It's also called the horizontal intercept. Okay. Now, what relevance does it have to this particular example? Well, it's the time when the ball hits the ground, right? So 1.75 is impact. It's also something else, though. 1.75 also represents the total flight time. Impact time, I should say. Total, I guess it's not really flying, but it's the total time that the ball is in the air. Okay, so those are 2 things that we might be interested in a projectile motion equation. This also tells you something about the domain. The applied domain for this, and notice that I said applied domain. Applied domain. Not the full mathematical domain, but the applied domain for this would be 0 to 1.75. And now why do we start? You can see that the function actually goes over here beyond 0, and would go over here as well beyond 1.75. But the point is that we don't care, because those are the limits those are kind of like the limits of our study. We don't care what happens before we started the clock, and we don't care what happens after the ball hits the ground. So that's going to be our applied domain. Okay. Now, good question. How do I actually find this 1.75 value? Well, we're going to study that later. So let me just kick the can down the road a little bit for that one, and we will come back to that issue at a later time. The range for this function, and again, this would be the applied range, which we're going to use in the application, right? Well, it's going to be from 0, because the range is the height, so it's going to be 0 height up to the top, which was at time 0. So at time 0, that's as high as we could get, so that would be 49. So it's going to be 0 up to 49. Now I can tell you right now how I got 49 is I just plugged 0 into the equation. I just calculated h of 0. That's easy enough to calculate, because you plugging in 0 is one of the easiest values to evaluate. Okay. So going back to this slide, I've sort of moved into talking about domain and range already. I guess the only thing that we should mention is this last sentence right here, the pure math function, domain and range. So what is that talking about? Well, if we are not limiting ourselves to thinking about a projectile motion problem, then the domain of that function, negative 16t squared plus 49, is all real numbers. So there's no restriction, and therefore my domain would be unlimited. Similarly, there's no restriction, since there's no restriction on the domain, that's going to change our range, and our range is now, it still would never go above 49, but it would go below 0, so we would go all the way down to negative infinity. All right. We've already seen some examples of this next slide of the two common question types, and that's good because this will maybe this will sort of help you to remember them. But the very two common question types that we work with in this class are given an input, what's the output, and given an output, what's the input. So if you recall from I think it was our last lecture, we were talking about this. The procedure that we use to deal with number one is vars, yvars. This is the calculator procedure. And then there's some other buttons, but that's how you start. So you're going to call up the function and evaluate it at an input. So, we're going to end up with y1 of something. For question 2, we use the calc intersect procedure. And there's a whole slew of buttons that go along with that, but they all kind of center around using calc intersect. So that's these question types are common enough that they deserve to be named and given a little extra attention. So there you go. Okay. So for example, in regards to the problem that we have at hand, if I ask you what is the baseball's height after 0.5 seconds, that's a type 1 question because I'm giving you a time, which is an input, and I'm asking you for a height, which is an output. So that would mean finding h of 0.5, or in the calculator, we would be running the vars yvars procedure. So that would look something like this. So I'd first have to enter the function. So let me clear all this. So I'd enter my function, negative, make sure you use the negative sign button for stuff like that and not the minus. So negative 16x squared plus 49, there's my function. And I want to do vars yvars, so I'll go to vars yvars, enter y1, evaluate 0.5. And oops, what did I screw up? It's great to see me screw up live on camera. I see what it is. I didn't actually need the I didn't need this right here because I used my squared button, so it doesn't need to also have the caret button. All right, let's try that again. Vars yvars function y1 0.5, enter, and we get 45 feet, as you can see here. Okay, now for a type 2 question would be something like this. When is the ball's height 25 feet? So that is an output, and we're asked for an input. We're asked for a time. So again, calculator procedure. We would need to graph the height 25. We also, in this case, you also kind of have to fool around with the window a bit. Let's change our window. Let's just change it to, I know since this is projectile motion and it's a baseball, it's not going to be in the air that long, so I'm just going to do 0 to 15 and zoom fit that. And that's too much time. Actually, that was way too much time because it's all bunched up right here. So let me actually change this to, let's change it to 0 to 5 and see what that looks like. Okay, that's better. Still actually too much time, but we can see the intersection point. And then we would go to second calc intersect. I'm about to run out of time in my video, so we'll have to pause here. There's your intersection value, 1.22.